9.3, we're taking a look at a couple of applications in probability. We encountered both of them last time that we're encountering period in this section. One of them was odds. We talked about odds a little bit. And the one that we left off on was called expected value. And let me pull up the screen that reminds you what expected value is. So expected value is taking a look at some kind of event that has numerical outcomes. Those outcomes are A1 through AN. So often it's money, doesn't have to be, but we use money as a lot of examples of this. And then the P1 through Pn is the likelihood that each of those events are going to happen. If we multiply each probability times their numerical outcome, and then we add those all together, that's the expected value. And we talked about a game as being fair if the expected value is 0. We did a couple of examples last time. I talked about a roulette wheel. We looked at the likelihood of landing on certain spaces, which was 1 out of 38 because there's 38 spaces. And then we had this sort of idea that we either win or we lose. And so the value that we get when we win, this is that numerical value, a sub 1 or whatever. And this is the probability that that happens. And the same thing is the numerical value. If we lose all our money. And then this is the numerical probability that that happens. We multiplied and we added them together. We had a similar setup for deal or no deal. And we're going to do an example one today, this lottery. So we have a given lottery. And in the lottery, we know that the odds of winning the lottery are 55 million to 1. Okay? We dealt with odds before. This is another statement where they're talking about odds. And it actually asks us on part A to figure out first what the probability of winning is. And we talked about the fact that people use odds and probability sort of interchangeably in language, but they're not exactly the same thing. So if you remember, probability means the likelihood that something happens compared to any possible outcome. That's what we're looking for in part A. Odds is when we're comparing the likelihood that something does happen to the likelihood that it doesn't happen, right? So we're counting as a part to part. That's what odds are, whereas probability counts part to whole. So the first question that's asking us is to figure out what the probability is, given that the odds of winning are 55 million to 1. So what would we do to find the probability of winning if those are your odds? What would we do? What does this phrase mean then? What does it mean 55 million to 1? What do you think, Avery? It's part to part. So we've got 55 million, we've got 1. Who's the winner? The 1. The 1 is the winner, and that means there's 55 million losers. Everybody with me on that? So you have 1 winner, 55 million losers, and do keep in mind that they've used this 55 with the word million afterwards, but that means like this, right? Correct? That's 55 million in its numerical expansion instead of its language expansion, okay? So the probability then is the person who wins compared to anything happening. So if there's 55 million people that lose and there's one person that wins, how many people total is that discussing or taking into consideration? 55 million 1. So the probability is 55 million 1 as its denominator. So 1 winner on top, 55 million 1 people total on bottom. Does that make sense? Okay. Then, where we actually get to the question is part B. If the grand prize is $14 million and a ticket costs $5, is the game fair? So fair is not mean like, that's not fair, right? Like that's not what we're talking about. Like we use it in language all the time when we sort of feel like an injustice is done to us for some reason. This has a mathematical meaning. It means, this question, is the game fair? It means the expected value is 0. That's the question that we're asked in there. That's the understood question we're being asked. So we need to figure out what the expected value is in order to answer that question. So the expected value is going to be, there's two outcomes possible. We either win or we lose. Everybody make sense of that? Okay, this is all assuming that somebody's playing the lottery to begin with. Otherwise, it doesn't even make sense to talk about, right? Okay, so if we win, there's a value that we win. And there's a probability of winning. But there's also added to that the likelihood or the value that happens when we lose. And we have the probability that we lose. Okay, does that make sense? Those are the only possibilities. Now, not every game is a win-loss. You're going to encounter some where you win a little bit in certain scenarios and you lose a little bit in other scenarios. So you could have more than two outcomes here, right? So like, let's say we did something with dice where we were rolling the dice, and if we get a 1, we win $1, and if we get a 2, we get $2, and if we get a 3, we get $3, and so forth all the way up. And then maybe if we get a 6, we lose it all, right? We get negative 10. Okay, so there's multiple outcomes in that scenario where we do win something, but we don't win in certain cases and so forth. Here, that's not the case. You either win or you lose. That's the kind of game this is. Does that make sense? Okay, so what do you win if you win? So you win 14 million, almost, minus your $5. And I'm going to write it in that way for us as well so that when you're looking back at this later, you realize what happened. You do win $14 million, but you paid $5 to play, which means it cost you $5 and you're out that $5. Now, what's the probability that you're going to win? Not 1/2. Oops, I didn't mean that. What did we have another thought? It's the number on top. That's why we did it. Part A. Part A tells us the probability that we win. 1 in 55 million and 1. That's the likelihood that we win. Okay, so what happens if we lose? What do we lose? We lose $5. And that means we're out $5 or it's a negative $5. That's the value difference in our pocketbook if we lose. It's minus 5. Okay, then so what's the probability that we lose? Because we don't have that one written down here, by the way. It's not flipping it upside down. If I flip this upside down, I get a number bigger than 1. Probabilities are always smaller than 1. It would be. As a fraction, there's an easier way to write that, though. Okay. How many people win? 1. How many people lose? Way more than 1 lose. 55 million people lose. Right? That's what that odds told us at the beginning. 1 winner, 55 million losers. Yeah? Okay. That's my numerator. 55 million people on top that lost or will be losing. What's my denominator? No, it can't be 1 because then I'm going to have a probability that's bigger than 1, but it's the 55 million and 1, which may have been what we meant. Yeah. Okay. So the 55 million and 1 is still the number of people who are playing the game in this case, or the number of tickets that were bought, or however you want to describe it. The 1 is the person that wins, and then the 55 million are the people that lose. Yeah? Okay. So taking a look at this then, we should be able to calculate this, and our calculator will be of assistance to us. This is actually 13,999,955 if we subtract that off. So if you want to write that down before you do your multiplication and so forth, that would be great. And then all the second part's the same. Okay, grab a calculator because you're going to need it to do that. You can find it all at once if you want. You can find it in pieces if you want. Either way is fine. So if I do 13,999,995 times 1 over 55 million and 1, I have 0.25 for the first piece. Did you guys get 0.25? Okay, good. Approximately. I'll keep more decimals than that, but that's the approximation. So I have 0.2545. Eventually I'm going to do this in terms of money, so 4 decimals is probably plenty for now. The other half needs to be -5 times 55 million divided by 55 million and 1. When I do that, I get -4.999. It's got a lot of nines. 9 repeating is what it looks like. Maybe it's exactly that. I'm not sure. But on the screen, it certainly looks like that for a long distance. And then I need to add these together, right? If I add these together, and remembering this isn't a dollar amount money, right? I would do 2 decimal places. I have -4.75. So that's what yours worked out to be? Okay. So what does that mean? Well, it means that if I played the lottery enough times, right? If I played the lottery enough times, the average cost to me per ticket would actually be $4.75. The real cost is $5, right? Assuming that I lose every time. But the average cost played enough times is $4.75. Now, I want to actually draw your attention to what that means that the lottery is doing with my follow-up questions, okay? Because this doesn't really intuitively make sense. Like, you can't really get $4.75 as a loss. Are you guys with me on that? This is an averaging thing. That's not what really happens. What really happens is that there's 2 outcomes. You lose the $5 or you win the 14 million. Those are the only 2 real outcomes that happen. So many state lotteries are actually, and they like to promote this way, said to benefit education. Have you heard that before? Nobody's heard that before. You know why you haven't heard that before? Because in your remembrance, the Oklahoma has always had a lottery, and we haven't always. The lottery came into play to benefit education. Does it look like it's going well for that? No. There's a very good reason for that, but I'll explain that in a second. So this is how lotteries come into play a lot of times, is they're said to benefit something that people want to have benefited, right? Like education. Everybody's like, yeah, let's benefit education. And so eventually you do this enough times, a lottery will pass and you get a lottery in your state. This is the way it works. The proceeds, under these conditions, if all the proceeds benefit education and 1 million tickets are sold, what is the expected value from the lottery? Okay, so the -475 is negative because it's to the consumer, right? It's to you if you go in and buy a lottery ticket. It's you that's losing the -475, right? Or losing the 475. So if you're losing it, who's gaining it? Well, whoever's running the lottery. In this case, it would be the state, okay? So you lose the 475, they gain the 475. Everybody with me on that? Okay, so if they're gaining it, it's actually a positive value, 475. And this premise is they sold 1 million tickets. So if you have 1 million tickets and your average gain is 475, and you multiply these together, you will gain $4,750,000. Okay, so the idea, as promoted, is that that money would go into the balance for education. Okay, all good? Okay. Now, that's not really possible, right? You're not really going to lose 475 and gain 475. That's an averaging feature. What are the real possibilities? Well, one possibility is that no one wins, right? The lottery comes and goes, they pull out the numbers, and nobody's a winner. And that happens all the time, by the way. And usually what happens then is that the jackpot goes up, and the jackpot goes up, and the jackpot goes up. So if you're seeing the jackpot going up, it means nobody's won. Okay, and in those times that they've been doing it. So if no one wins, then what really happens is that the state keeps all $5 of that for the 1 million people who bought it. Nod your head if that makes sense. Nobody wins, so they keep the $5 million, that's what this ends up being, that was made by the sale of those tickets. So it's a $5 million bonus. Secondly, there's an option that says someone wins. Now you might say, well, can't you sometimes have multiple people win the lottery? They do, but when they do, they just split the jackpot. So it doesn't really matter if you say one person wins or a whole bunch of people wins. The amount's still the same. Everybody good with that? Okay. So if someone wins, they've still had $5 per ticket that they have brought in as income, correct? But what do they have to pay out then? Well, the jackpot. What was the jackpot? It was 14 million. Okay, so what happens when I take 5 million and I subtract 14 million? Somebody said it. What's 5 million minus 14 million? Okay, what's 5 minus 14? 9, thank you. It's negative. It's 9 million, negative. So it's negative 9 million. These are the two possibilities. We either have, oops, sorry, touched the wrong button. We either have a positive 5 million put into the fund, or we have a negative 9 million, so we have 9 million taken out of the fund. These are the options that happen. So here's the conundrum that you should feel when you see something like this in terms of promotion of a lottery. And then we're going to briefly just tell you what happens for real with the education and why this never really works. The conundrum is you either have to hope that everybody wastes their money buying tickets and nobody wins. That's how you get the 5 million, right? Or you have to be okay with the fact that somebody does win, they didn't waste their money, but it didn't actually benefit the fund that they said that it was going to benefit. Do you see the dichotomy there and how you can't really root for one or the other? You're either rooting for education to get the money, which means you're rooting for everybody to lose their money at the lottery, or the opposite of that. So here's what actually really happens when there's a fund that's set up like this, and this is why it doesn't work, and it's why it's not worked in Oklahoma. This is what happened in Oklahoma, by the way. We have a lottery. It's said to benefit education, is that when the state legislature actually does the budgeting for the state, then they just allocate less money to the state to begin with, to the education to begin with. Right? So they're saying, okay, well, they're going to get this amount of money from the lottery, so we can just spend this amount of money on something different. That's really what happens.